Hey guys, today in this video we're going to be doing some civil FE exam review, and we're going to be focusing specifically on dynamics today. So I do have a practice problem for you all, but before we get into that, if you are looking to pass your civil FE exam, look no further than this channel. Go ahead and hit the subscribe button, turn on those bell notifications so you know exactly when I post. And do not forget to check out some of the free resources linked down in the description box below. On this channel, I do a ton of practice problems and go through each of the topics that are going to be on your civil FE exam. So let's go ahead and look at our practice problem for today. All right, so this one says a dumbbell consists of two uniform spheres of mass M and radius R, joined by a thin rod of mass M, length L, and radius R. See diagram. Okay, I see a diagram below. What is the moment of inertia about the center of mass and perpendicular to the rod axis A? Okay, a lot of information here. Before I do any problem, I always ask myself, can I use the reference handbook for this? And in my case, it's asking, what is it asking for? It's asking for the moment of inertia about this object. So I know that in my reference handbooks, there are some formulas for moment of inertias. I know that looks like I have a rod coming in this along the center, and then I have two spheres on the outside that make up my dumbbell. All right, so where do I start? Well, I'm gonna start with finding my total moment of inertia. So start there. Just say my inertia total is equal to what? All right, so my total inertia is going to be, I'm just going to break it up, right? Break up this big object into separate, smaller pieces. So I'm just going to say it's going to be the inertia of sphere 1, all right, about the a-axis, because that's really important. All right, then I'm going to add, let's just put both of the spheres beside each other. That way it's simple. So sphere 2 about the a-axis. And then we have the moment of inertia of the rod. All right. So that's going to be my total moment of inertia. So now that I know that, where do I go from there? Well, what is the moment of inertia of a sphere? Okay, so can I use my reference handbook for this? The answer is absolutely. So if you want to do like a control find to get to the chart that you will need, you can do that. Search for that. I already know where it's at, which is nice, but it's going to be in the dynamic section at the time that I'm recording this video. And there's going to be a chart with different figures. This, you can see we have a rod, some hollow structures, some cylinders, and we have the sphere, right? So in this case, we have a sphere that we need, and it's important that you know the kind of what these headers are. So you got your mass and centroid for formulas. You got the mass, moment of inertia, and then you have even things like your radius of gyration, which we're not solving for that, but just important to note if they ask you that. Okay. And so we're going to be looking at mass, moment of inertia, that portion of the chart. All right. So we'll just start with our first object, which is our sphere. Okay. So sphere 1, all right, about our axis A. So looking at this chart, we need to compare our problem with the chart that we're given. So out of these 3 different formulas, the inertia about X, inertia about Y, inertia about Z, which axis are we going to be choosing? Or which formula are we going to be choosing? Okay, so we got our sphere, and it looks as if we're not going to be choosing the inertia about our x-axis, and let me explain why. So in our figure, we're using axis A in our problem. From this chart, this axis X looks to me exactly like axis C in our problem. So it's basically going, parallel with our radius, arrow. So we're not going to be using that. Axis Z, no, we're not going to be using that. Axis Y is what we should be using, and it looks very similar to axis A. It's just like going straight up from our sphere. So we're going to choose the moment of inertia at axis Y, and that C, that IYC, that C just stands for the center of your object. So in this case, it's the center of our sphere. And you can see in our chart, that point, it has that little C right there, and that's the center of our sphere. So we're going to use IYC, which is going to be, in this case, 2 M R squared divided by 5. Okay, but we are not done yet. We are not done yet. The next thing that we need to do is apply something called the parallel axis theorem. So we would be done in this case if we were trying to find the moment of inertia about the center of our sphere. But this is a whole dumbbell. So we're trying to find the moment of inertia about axis A. So we need to use the parallel axis theorem. I'm just going to call it PAT. And what does this mean? Let's look up the parallel axis theorem. You can just search for it in your FE manual. And I'm currently searching. Okay, so I got moment of inertia, but we want to go specifically to the mass moment of inertia. So that's what we're currently using. Okay, so it basically says your new moment of inertia of your object is going to be the moment of inertia about the center of your mass, which in this case is our sphere, plus md squared. So I see, and hopefully you all have seen this before, but I'm just trying to make it like as clear as possible what we're doing here, because I know some professors are really confusing. Okay, so I sub c plus md squared. So our FE manual helps us to really know what these symbols and all this confusing like terms means. So we'll break it up. And this is why it's important to really understand your manual. So you got I sub c. I sub c is, and I'll just scroll over a little bit so you can see. It's the mass moment of inertia about an axis that is parallel to the above specified, and that says axis. Okay, so what does that mean? And it says but passes through the body's mass moment. So hopefully you're following along with me. Kind of could zoom out. Okay, so what does that exactly mean? Well, it's just basically saying that you're taking your sphere and there is a parallel axis that we're using, and it is our parallel axis was that y-axis that we chose to take our to find our inertia about, and we're using that mass of our sphere, and then we're going to add our m. We're going to add our m times d squared. So what is our m? It's the mass of the body. Okay, so just the mass of the body, which is the mass of our sphere, plus or times d. What is d? It's the normal distance from the body's mass center to the specified axis. So it's that distance from the center of the sphere to the a-axis. So how do we get that? We're going to add, okay, we know mass is just mass. I'll just put an M for that. Okay, what is D? All right, so it's the center of our sphere to the axis A. So the center of our sphere, we're going to go from the center of our sphere and we're going to say R. We have R and L that we can use as kind of our point. So we're going to say R is just the radius. Okay, so we've reached now the center of our sphere to the end of our sphere. And then we have a little more ways to go to get to our axis A. So then I'm going to add the length. But if I just add the length, I'm going to be at the edge of the other sphere. So I've gone past my x-axis. So I need to divide that length by 2 to go from the center of my sphere to my x-axis. Okay. So this in parentheses, the r plus L over 2, that is my d, my distance, my normal distance. And then we have to square it. All right. And so if you're a little confused, this portion is my I sub, so this portion that I circled is my I sub c. Just basically the moment of inertia about my sphere and its center, plus m, same m's, times my d, which is r plus L over 2 in parentheses, and then I squared that. So this is d squared. Okay. So hopefully that makes sense. So that alone is our inertia about the a-axis for our first sphere. Okay. To save some time on this, I know that my second sphere is uniform. So that means it's the same mass, same, shape, and it's also the same distance from my axis A. So I can multiply my inertia, the moment of inertia about my sphere 1 and multiply it by 2 to get the sphere, both moment of inertias of both spheres. So I got the inertia of one sphere, but I just was going to multiply it by 2 because it's the same for that second sphere on the right side. Okay. So now we're left with, so we've taken care of inertia sphere 1 about the a-axis, inertia sphere 2 about the a-axis. What's left is the inertia, moment of inertia of the rod. Okay. So how do we get that? Well, we go back over to that chart, search for, just going to pull it back up. And all right, we got our slim rod here, and now we just have to choose the right formula, right? So if we look at our chart and we look at the mass moment of inertia and we see the I sub x, if we're doing inertia about the x-axis, that would be the same as from our problem axis C. So this is not what we want to take because we're looking for about the axis A. So the only one that I can see that matches what we need would be taking the moment of inertia about the y-axis going straight up. And so that would be I y sub c, which is equal to, well, in this case, it looks like it's the same as the z-axis, but we're specifically focusing on the y-axis from our chart. All right. So we're going to be using ml squared over 12. ml squared divided by 12. All right. And so now what I'll ask is, are we done? Or do we need to use the parallel axis theorem again? You can pause this video if you want to and answer this yourself, but the answer is no, and I will explain why. So in our diagram, the center of this rod is at point C, right? I'm over here pointing at my computer. It's kind of hard to point C. Okay. That's the center of my rod. And that's where that's the axis that we're using about the center of our rod. And so in our problem, axis A is at the center of our rod. So we took the moment of inertia about the center of the rod from our chart and for our problem. So there is no distance d that is, from the axis that we chose to take from the center versus the center of our rod. So that D is going to be 0 in this case. And so, of course, we have a mass, but any mass times 0 is going to cancel out. And so you're just left with the inertia about the center of our rod. So you wouldn't need, all in all, you wouldn't need to use the parallel axis theorem. This is really conceptual, very, very conceptual. So I hope this problem, wasn't super confusing, but this is something that you will in fact be tested on the exam. If you found some value out of this video, make sure you hit that like button, hit the subscribe button, and don't forget to take advantage of those free resources linked down in the description box below. Also, I have created a full, complete self-study guide where if you're finding problems like this to be a little challenging and you want some more practice with things like this, then you can check out the links. I've created this study guide to have links to over 300 practice problems, videos with clear solutions, even practice quizzes that is going to help you just literally crush your Civil FE exam. So make sure you all check that out. And in our next video, I'm going to be doing some more practice problems on dynamics. And I think it's going to be force acceleration. It's literally the next topic from the reference handbook. But hope you all enjoyed this video, and I will see you all in the next one. Peace.